Hello everyone. Today we will see the algebra of a complex number. Okay. So, let's have any complex number z1 is equal to a1 plus ib1 and z2 is equals to a2 plus ib2. Now, first discuss one by one. First discuss the addition of a complex number. Addition of a complex number. Clearly, addition is z1 plus z2 is equals to a1 plus a2 plus I times b1 plus b2. Now, if we talk about the vector point of view, so as we discussed that complex number, if we want to analyze complex number, the two ways. One is using the Euler number, other is using the vector, 2D vector. Okay, if you want to analyze the complex number geometrically, then Euler form or the vector representation as a 2D vector, they come easy to analyze, or you have the we can easily visualize the complex number. Okay, let's visualize the addition. So let's say any complex number here, this is, let's say, z1 and this is z2. So it's similar to if, let's say, we have the vector oa and let's say we want to add the vector OB, let's say vector A, this is vector B. So addition of vector A plus B is nothing but lie along the diagonal of a parallelogram. Okay, they lie along this. So this is vector A plus B. So we should know that the A plus B is along diagonal of parallelogram formed. Okay, same way in complex number also, the addition of same in complex number also, the addition of z1 plus z2 will lie along the diagonal of a complex number form. Okay, so this is the z1 plus z2. So this, let's say, z1 is a1 plus ib1 and z2 is a2 plus ib2. So this z1 plus z2 will be a1 plus a2 plus I times b1 plus b2. So this z1 plus z2 will lie along the diagonal of a parallelogram. Okay. So let's say this z1 vector, z2 vector, and z1 plus z2 is we form a parallelogram with the sides at z1 and z2, and then the addition is nothing but the diagonal of parallelogram. Okay. Now if you talk about the subtraction, let's talk about the subtraction of a complex number. Subtraction again same. If I say, let's say, z1 minus z2, so obviously a1 plus ib1 minus a2 plus ib2. So z1 minus z2 will be a1 minus a2 plus I times b1 minus b2. Pretty easy. But if you talk in terms of the geometrical representation of this subtraction, this is same as the vector. Just like, let's say, any vector. Let's say we have the vector a. This is vector A, and let's say this is the vector B. So vector A minus B. So what we'll do? This is, let's say, this is minus B, and then we have A minus B will be along the diagonal of this parallelogram. So we'll form the parallelogram here. So the parallelogram will be formed something like this. So this one. Okay, this is A minus B. So A vector minus B vector, and also observe that A minus B will also be along this one. A minus B. Why? Because in mathematics we treat vector as a free vector. So this, if this is, let's say, this is O and this is this vector A minus B and this vector A minus B, they are parallel. Okay, so these are same. Same way in complex number also. Let's say this vector is z1, this vector is z2. So clearly z1 minus z2. So I will draw like this. This is minus z2, and the will form a parallelogram with this. Okay. So this one. This is z1 minus z2. Okay. So this is z1 minus z2, and also this is same as this also. Here also I can write like this: z1 minus z2. Okay. This is called a subtraction. So by the way, if we have any complex number, let's say like this very interesting things. Let's say complex number z1. This is complex number z2. So the addition of this one will be one of the diagonal. This addition will be one of the diagonal of a parallelogram z1 plus z2, and the subtraction will be the other diagonal of parallelogram. This is the z1 minus z2. So if z1 and z2 are the sides of parallelogram, then the two diagonals, so one of the diagonal will represent the addition and other diagonal will represent the subtraction. Okay, now let's talk about the multiplication. Multiplication of a complex number. Okay, so multiplication is also, let's say, any complex number z1 into z2 is equal to a1 plus ib1 into a2 plus ib2. Okay, so if you multiply this complex number, I will get a1 a2. So a1 a2 and minus b1 minus b1 b2 plus I times a1 b2 plus a2 b1. Okay, this is simple algebra. But what is the representation? If you want to represent this multiplication, that becomes a little bit interesting. Okay, so let's have a very complex number here. Let's say this is z1. So let's say z1 is equal to r1 e to the power I theta 1, and z2 is equal to r2 e to the power I theta 2. So z1 has a theta 1 and r1, and z2 complex number has the argument theta 2 and the modulus r2. But if you multiply, observe that multiplication nothing but r1 r2 e to the power I theta 1 plus theta 2. So multiplication will have a modulus r1 r2, but interesting thing is the argument. Argument of z1 z2 is theta 1 plus theta. That's quite interesting. So argument is z1 plus theta 1 plus theta 2. So where does this lies? So this lies along the here. Why I am drawing it here? Because this already is theta 2, and the argument of z1 z2, argument of z1 z2 is theta 1 plus theta. So this already is the theta 2. I will add theta 1. Okay, that's why now this argument of this z1 z2 is theta 1 plus theta 2, and obviously the modulus is r1 r2. Okay, this is how we represent the multiplication in terms of the Euler form. So as I discussed in the beginning of lecture, it's easy to either treat as Euler form or treat as a vector. Okay. Okay. Now talk about the division. Division of a complex number. Okay, so division is also algebraically we can say that the z1 upon z2 is a1 plus ib1 upon a2 plus ib2. Since we want a complex number should be in the form of a plus ib, so we will rationalize this part, and a1 plus ib1 upon a2 plus ib2 we multiply with a2 minus ib2 upon a2 minus ib2 multiplied with, that is called rationalization. So we will get something I can directly write. So it's a a1 a2. So let's say a1 a2 plus b1 b2 plus I times a2 b1 minus a1 b2 divided by a2 square plus b2 square. So this is in the form of, this is the real part and this is the imaginary part of the complex number. Now let's discuss the its geometrical interpretation. Okay, let's say this is the real axis, this is the imaginary axis. Somewhere z1, so let's say, see, interesting, z1 is r1 e to the power I theta 1, and z2 is r2 e to the power I theta 2. So what is z1 upon z2? The modulus will be r1 r2, and z1 z2 will see I theta 1 by theta 2, which will get theta 1 minus theta 2. So interestingly, the argument is interesting. Argument of z1 and z2 is theta 1 minus theta. That's quite interesting. So argument is z1 theta 1 minus theta 2. Let's see if we draw the complex number. Let's say z1 having argument is theta 1. Let's say z2 having argument is theta 2. Okay, now theta 1 minus theta 2, theta 1 minus theta 2. ठीक है, so where does this lies? Okay, let's see. It's interesting if I draw like this, otherwise we have to draw the negative side. So uh, let's say hmm, okay, let's say this is z2 having argument theta 2 and modulus r2, and let's say this is z1 having argument having modulus r1 and argument theta 2, sorry, theta 1. Now what is saying that the argument of this is theta 1 minus theta 2. So what happens, I will draw somewhere this is theta 2, so from theta 1 I will subtract. So let's say this is a theta 2. Okay, so this whole is theta 1 and this theta. So what about this one? This is nothing but theta 1 minus theta 2. So this z1 upon z2 will lie along the somewhere between z1 and z2. So this is z1 upon z2, and obviously its modulus is r1 r2. Interesting. See, in case of multiplication and division, the interesting is the direction, not the modulus, because it may be, because depending on whether r1 r2 is greater than 1 or less than 1, the multiplication may be lower or higher, no? Because you can't think that this z1 z2 is has a modulus greater than z2 or z1. Okay, because if, see, the thing is, let's say, what I mean to say that, let's say the argument r1 is 1 by 2 and r2 is also 1 by 2, but what's division? 1. Okay, because that means this is greater, z1 upon z2 has a greater value, whereas if let's say the r1 is 4 and let's say r2 is 2, so what is r1 r2? Let's 4 upon 2, that is equal to r2. Okay, so it may not necessary that they are greater than the modulus of z1 upon z2 is greater than the corresponding z1 and z2, or lower or equal, doesn't matter, because they're depending on the values of r1 r2, whether they are greater than 1 or less than 1. Okay, but interesting thing is the argument is important, direction is important. Same way in the multiplication also you should observe that this particular z1 into z2, the modulus, it may be greater than the corresponding z2 or z1, or it may be lower than the corresponding z2 and z1. But the important thing is their argument, their direction, that is important in case of multiplication and division. Okay, so this is how we do the multiplication and division of a complex number. Okay, so we'll see in detail about all these things when we study the properties of the argument. Then this multiplication and division will be very interesting. Okay, so let's talk about the next algebra, that is the mm, equality. Let's talk, next part is the equality of a complex number. That is also very interesting. Equality of complex number. Okay. So equality of a complex, say Z1 is equal to Z2, two complex number are equal. So if two complex numbers are equal, so interesting, two complex numbers are equal, their real and imaginary part are equal. So if I mean if two complex numbers are equal, okay, if two complex numbers are equal, we should note down that then first the real part of z1 is equal to the real part of z2, and this is and not or, and the imaginary part of z1 is equal to imaginary part of z2. Okay, that is both has to be true, both has to be true, has to be true, important thing, both has to be true. Okay, that means we can write like this. So the modulus equal and argument should be equal. Okay, that means that both real and imaginary parts are equal, or their modulus and their arguments are equal. So when the problem will arise, we will use either of them. We can either use the corresponding real and imaginary parts are equal, or corresponding modulus and argument. So we will use depending on the problem. So we use uh, so depending on problem, use either this one, depending on problem. Which problem? Depending on problem, use either one or two. Okay, ठीक है. And let's talk about the inequality of a complex number. So next is inequality of a complex number. Inequality of a complex number. See, the problem is if someone say Z1 is Z2. No, this is inequality. But important comparison between the two complex numbers are not allowed. Okay. Basically, they are allowed only if the complex number are purely real. That means what I mean is that if someone say any complex number, let's say Z1 is equal to 4 and Z2 is equal to 6. So we can say that Z2 is greater than Z1. That is absolutely fine. But if I say, let's say Z1 is equal to 4i and Z2 is equal to 6i. So if you can't say that Z2 is equal to Z1, this is wrong. Okay, the inequality of complex number is in general is not defined, they're only defined if they are pure real. So what I mean says, you can note down that the comparison of two complex number, comparison of two complex number are allowed only if uh, both are purely real numbers. Only then they are allowed. Okay. So someone say z1 is equal to 2 plus 3i and z2 is equals to 6 plus 9i. So we can't say z2 is greater than z1. This is wrong. Okay. The comparison of complex number is not, in general, inequality is not defined in complex number. Okay. Why it is happening? Because see, the thing is complex number is a point. We can assume that the complex number is a point we have discussed, is a point, or we can have a vector. Complex number is a point or vector, and we can't compare two points. Okay, and we can't compare two points. Got it? What I mean to say that, let's say somewhere is the point here 2 comma 3, let's say point is 1, q point is 4 comma, let's say 1. So we can't compare, we can't say that a p is greater than, this is wrong, we can't compare the points. Okay, same with the vector also we can't compare. Let's say this is, let's say vector a, This is vector B. Can't say B is greater than A. This is wrong. We can't compare vectors or point. We can compare their magnitude is possible. See, the interesting thing is we can compare the magnitudes. That is the interesting thing. So we can only compare. We can only compare their distances. That is magnitude. Okay. Just like in this case, let's say we have the any point is here. Let's say this point is P and this point is Q. Let's say O. This is, let's say, 4 comma 3. This is, let's say, 2 comma 5. We can't say point P. That means we can't say that the 4 comma 3 is greater than 2 comma 5. This is wrong. But yeah, we can compare the distance, that is OP. So what are the distances? Let's say OP is 4, 4, just 16, 3, 3, 9. So it's 25. Okay, OP is 25. And OQ is 5, 5, 25, 4, 29. Sorry, 5 and 29. Okay, so we can compare we can say that the OQ is greater than OP, but we can't compare the distances, points. Same in vector also. See, let's say this vector is A and this vector is B. So we can't say that vector A is greater or B is greater than A. But we can say that the magnitude wise B is greater than A. Okay, this is fine. This is not fine. Same in complex number also. If someone says that the Z1 is greater than Z2, in general this is wrong until unless Z1 and Z2 are purely real numbers. But yeah, we can compare this one. This is absolutely fine. Z1 is greater than Z2. Okay, because now they are the pure real numbers or they are the magnitude. So its comparison is possible in case of the magnitude, not their corresponding value. Okay, so so let's talk about the. Let's take some examples. Okay, for example, let's take one example. Uh, one very basic example. Let's say we have asked question is find ordered pair, that is xy. Let's say xy for which x square minus y square is equal y square minus I times 2x plus y is equals to 2I. Okay, so clearly we can use the equality of the complex number here. Okay, so we can compare the real and the imaginary part and solve. So here the real part is, so comparing the real part of left hand side is equal to real part of right hand side. Similarly the uh, Similarly, the imaginary part of left hand side is equal to imaginary part of right hand side complex number. So we'll say x square minus y square is equal to 0 and 2x plus y. 2x plus y is equals to minus 2xy plus y is equals to 2. So we can solve it. So from here I can see that this is nothing but x is equal to plus minus y, and from here I get 2x plus y is equal to minus 2. So we can take the case one is that x is equals to y. If x is equals to y, I will get 2y plus y is equals to minus 2. Hence, y is equals to 3. So, minus 2 upon 3. And similarly, x also 2. So, in this case, x is equals to minus 2 by 3 and y is equals to minus 2 by 3. So, what is the ordered pair? So, in case 1, the ordered pair is minus 2 by 3 and minus 2 by 3. Now, case 2, when x is equals to minus y. Case 2, when x is equals to minus y. So it will give minus y means 2 minus 2y plus y is equals to minus 2. So you get minus y is equals to minus 2 or y is equals to 2. So x is minus y. So the x will be minus. The ordered pair is minus 2 comma 2. This is the ordered pair for the case. Okay. Okay, so this is how we can use the equality of the complex number to find the particular solution, solving some ordered pair. This one. So by the way, one important things, very interesting things we should, well, not that much important, but you should note down. Uh, See, we never say that a positive complex number or negative complex number. Okay. Suppose if I say that if let's say I say z is equals to minus I. Okay, obviously fine. But we will again. It is wrong to say. It is wrong to say negative imaginary number. Negative imaginary number. Okay. Why it is wrong to say negative imaginary number? Because complex number inequality is not defined. So negative positive means what? If someone says z is greater than 0, that means z is positive. Okay. If z is less than 0, we'll say z is negative. Got it? But the problem is this thing is not defined. This is not defined. Inequality is not defined. Inequality is not defined in complex number. That's why whenever we talk, we never say negative or positive complex number. We never say negative or positive complex number. Okay. So these are something basic property, basic algebra of a complex number. Again, one before ending, just I can say one important things here. As we are talking about the see, if I say a question, let's say question. Let's say if z1 is equals to z2. Okay. So and z1 is equal to z2, then and let's say z1 plus z2 is equal to z1 minus z2. So if I ask you what is the argument of z1 uh, upon z2, okay. So see, in this case, if I say z1 and z2 are equal, any complex number, this z1 and z2 are equal. Okay, z2 are equal, and they are saying that the addition and subtraction. So what is z1 plus z2? These are equal. Z1 plus z2, and this is z2 minus z1. Okay, so essentially what does it mean? It means that the diagonals are equal. Diagonals are equal. Okay, so diagonals are equal. Essentially diagonals are equal because these represent diagonals. And what does this means? This means sides are equal. So diagonals are equal and sides are also equal. That means which kind of geometry is this? It is a square. Okay, so let's say this is z1, this is z2. Okay, so the distance z2 is this one, distance z1 equal, and essentially we have the this is z1 plus z2, this diagonal, and this diagonal is z1 minus z2, as I discussed in the beginning of lecture. Now they say that these are equal. These are equal. So what is the argument of z1 minus z2? Argument of z, what is argument of z1 z2? Argument of z1 z2 means see, we discussed already. Let's say we have somewhere is the z1, and let's say this is the z2. So this is theta 1, this is theta 2. So argument of z1 minus z2 is the angle between z1 and z2. Na? See, recall that e to the power I theta 1, e to the power I theta 2. Argument of this. So this is nothing but, let's say this is r1, r2. So argument we can write r1 by r2 e to the power I theta 1 minus theta 2. Okay, so we have to find the argument of this one. So argument of this is nothing but the theta 1 minus theta 2. That is the theta 1 minus the angle between z1 and z. Theta 1 minus theta 2 is the this one angle. Okay, so angle, that is theta 2 minus theta 1. So I can write minus theta 2 minus theta 1 here. So essentially the theta 2 minus theta 1, that is argument of z1 minus z2, is the angle between these two complex numbers z1 z2. So clearly here this is z1, this what the angle between this one. Angle is pi by 2 or plus minus pi by 2 depending on which is greater. So I can say in this case that argument of z1 upon z2 is equals to we can either plus or minus pi by 2. Okay, so this is how we use this algebra of a complex number, especially geometrical meaning, to solve some of the problem without doing any analytical work. We just need to understand what does these addition, subtraction, multiplication, division represent. Using that concept, we can easily solve the problem. Okay. Okay, so I am now ending the class here. So thank you for your attention. So we'll next see some other concepts. Okay. Okay.